Pythagoras was a Greek mathematician who lived around the 6th century BC. He developed a theorem that said a squared plus b squared equals c squared for any right triangle. So if you have a right triangle like this, and two of the legs make an angle of 90 degrees with one another, then you can show that a squared plus this side squared, the length of this side squared plus the length of this side squared, is equal to this squared. So we're assuming Euclidean geometry. We're not assuming a non-Euclidean Einstein geometry. So that's an axiom to start with. And so if you extend out this distance here, if you extend this distance out this way, 90 degrees to this leg, and then extend this leg out a distance b, and similarly for c at 90 degrees to the hypotenuse, then the area of this big square will be equal to c squared. The area of this here will be a squared. And the area of this square will be b squared, right? And so one could show that this, if we cut this square out, picked it up and set it inside here, it might do something like, or it will do something close to this, right? It'll fit in here just like that. And then we cut this guy up into, some pieces, into some strips. We could fit this guy along here, and this guy would fill up this perimeter area. So this area plus this area will fit into this area. So that would be the geometrical proof if one were to go through it rigorously. But one could go through this empirically, because if a squared plus b squared equals c squared, then and if you have a piece of paper that has an even mass distribution, right? The mass distribution is planarly even, so it's not like lumpier in one part of the paper than it is in another part of the paper, then you could simply cut out this square here and cut out this square and weigh them, say with a postal scale that's capable of measuring, on the order of grams and fractions of a gram, and then cut out this one, right, and weigh this one, and they should weigh the same. So this plus this, the mass of this plus the mass of this will be equal to the mass of this. So this would be sigma times a squared plus sigma times b squared, where sigma is the mass density being in grams per inches squared, and we see that when we multiply times the area, which is in inches squared, and this is a 2 right here, that the inches squared cancel and we get mass, right? So we're left with grams. So then this is equal to sigma times c squared. So the mass of A plus the mass of B, put this a little bit lower, mass of A plus the mass of B will be equal to the mass of C. And if you show this for a number of triangles, you should do triangles of all different sizes, right? So take a piece of paper and do some small triangles. There has to be an angle of 90 degrees here, and so there's going to be some error in your analysis, right? Some empirical, whether or not you get the angle exactly right, this 90 degrees, whether or not the two legs are exactly 90 degrees to one another. But you could use graphing paper, engineering paper, and it would work really well. Engineering paper has got blocks on it that makes it easier to draw straight lines and so forth, and to scale things properly. And you could, buy postal scale and verify this, and you will have verified the Pythagorean theorem empirically. So it's perhaps a good science project for a child or something like that. So at any rate, this is the Pythagorean theorem. It was done in about 600 BC, and it's a good one to know. We will use it extensively in Physics 1 and Physics 2. So it shows up in vectors. We need to use it with vectors, vector analysis, and also geometries of different situations. It's a good theorem to have on hand. So know it and know it well. So I'm going to step aside and give you a clear screenshot.